You know, at the very heart of so many things, we're talking everything from the hemoglobin in your blood to powerful industrial catalysts. You'll find these things, coordination compounds. Now, I know they look super complex, but they're actually built on just a few simple rules. So, over the next few minutes, we're going to pull them apart and see exactly what makes them work. Let's dive in. So, meet our main character for today. See that metal ion right in the middle? It's surrounded by a whole crew of other molecules. Yeah, it might look like a bit of a chaotic tangle at first, but stick with me. By the end of this, I promise you'll see the elegant, simple logic that's holding this whole thing together. All right, here's our roadmap. First, we'll figure out what these things actually are. Then we'll meet the core components, learn the rules for building and naming them, get into a really cool plot twist about their structure, and finally, we'll figure out what makes them so darn stable. Okay, let's kick things off with the core components. Before we can really get the whole picture, we need to get to know the individual players, the cast of characters, if you will. So what exactly are we looking at? Well, at its heart, a coordination compound has a central metal atom that acts kind of like an anchor. And clustered all around it, you've got these other molecules or ions we call ligands. The special connection they share? It's called a coordinate bond. It's the glue holding the whole shebang together. So what are these ligands? You can think of them as being really generous. See, each ligand comes to the party with a pair of electrons that it just gives, donates to that central metal atom to form the bond. In the world of chemistry, this makes them what we call a Lewis base. They're the givers. But you know, not all ligands are created equal. You've got your monodentate ligands. Think of that like a single simple handshake. It only binds at one point. Then you have bidentate ligands, which are more like a two-handed grab. And polydentate ligands, oh, they're like a full-on octopus, wrapping around the metal with multiple arms. And you can see this perfectly right here. On one side, you've got simple monodentate ligands just making one connection, but then you have something like EDTA on the other side. It's so big and flexible that it can just wrap itself around the metal and form a bunch of bonds all at once. That's the octopus hug we were just talking about. Okay, so we've met the players. Now let's crack open the instruction manual. How do these pieces actually come together, and more importantly, how on earth do we give them those long, complicated-looking names? So the very first rule you need to know is something called the coordination number. It sounds really fancy, but it's not. It is literally just a head count of how many bonds the ligands are forming with the metal. And this number, well, it's everything. It's the key that decides the final 3D shape of the whole molecule. And check this out. The relationship is super clear. A coordination number of 2, bam, you always get a straight, linear shape. A number of 4 usually gives you either a tetrahedral shape or a flat, square planar one. And a coordination number of 6, which is super common by the way, creates this absolutely beautiful, symmetric octahedral shape. Now for the naming. I know these names can look pretty intimidating, but trust me, it's just like learning a simple code. There's a set order. First, you name the ligands alphabetically. You toss in prefixes like di or tri to say how many there are. Then you name the metal, and you put its charge in Roman numerals right after. That's pretty much the core of it. Let's try it out on a real one. See this example? We've got 4 amine ligands and 2 chloro ones. Okay, so alphabetically, amine comes before chloro, so we start with tetraamine, then dichloro. The metal is cobalt, and we figure out its charge is +3, so cobalt 3. See? It's just a logical puzzle. Okay, now for the real plot twist. What happens when you have the exact same chemical formula, the same list of ingredients, but they're just arranged differently? This, my friends, is the incredibly fascinating world of isomerism. So isomers are basically chemical twins with totally different personalities. They are made of the exact same atoms, the same formula, but just because those atoms are put together differently in 3D space, they can end up with completely different colors, different reactions, different everything. And isomers really come in 2 main flavors. On one hand, you have structural isomers. This is where the atoms are fundamentally wired together in a different order. Then, on the other hand, you have stereoisomers. Here, the wiring diagram is exactly the same, but the parts are just twisted into different shapes in 3D space. So, if we dive a little deeper into structural isomers, you can see there are a few different ways that wiring can get scrambled. We're just going to focus on one really cool example to give you a feel for how this works. And this is a perfect example. It's called linkage isomerism. You see, this ligand here can connect to the metal through its nitrogen atom, which makes a nitro complex. Or it can flip around and connect through an oxygen atom, making a nitrito complex. It's the same exact ligand, just a different connection point and a totally different isomer. Wild, right?
Okay, now let's talk about stereoisomers, where the wiring's the same, but the 3D shape is different. The first type is called geometrical isomerism, and it all comes down to where things are. If two identical ligands are neighbors, right next to each other, we call that cis. If they're on totally opposite sides of the metal, we call that trans.
And you can see it plain as day right here. In the cis isomers, see how the identical ligands are side by side, kind of like they're sitting next to each other. But in the trans isomers, they're directly across from each other at a 180-degree angle. It's such a simple spatial difference, but it has huge consequences. All right, get ready, because the other type of stereoisomerism is a real mind-bender. They're called optical isomers, and they are perfect, non-superimposable mirror images of each other. The best analogy? Just look at your own two hands. They are mirror images, but there's no way you can stack them to be perfectly identical.
This shows it perfectly. Look at the molecule on the left. Now, the one on the right is its exact reflection, as if in a mirror. But no matter how you try to twist or turn that right-handed one, you could never, ever make it look exactly like the left-handed one. They are fundamentally distinct left and right versions.
Okay, so we know how they're built, we know the different shapes, and even the weird plot twists they can have. But what actually makes a coordination compound stable? What are the forces that bind everything together so tightly?
Well, it really just boils down to three main things. First, the metal itself. The smaller it is and the more positive its charge, the more powerfully it pulls those ligands in. Second, the ligand. The better it is at donating its electrons, the stronger the bond will be. And finally, there's this really powerful idea called the chelate effect. And all this says is that those multi-armed octopus ligands form way more stable complexes than the single handshake ones. That big hug really locks everything in place.
So there you have it. We've gone from the basic building blocks and naming rules all the way to the strange, fascinating world of isomers and the forces that hold everything together. It's really a whole system of molecular architecture, and it's all governed by a pretty clear set of principles. So, my question for you is this: now that you know the rules, what could you build?